Next, we have Peter Robinson, and Peter is going to tell us about the tether stresses and the atmosphere problem.
I've just got a few slides talking about tether stresses and then moving on to the atmosphere problem. Now, these equations are in the 2013 book, and most of you are probably familiar with them, the equation for the area and the taper ratio for the main tether. But these are equations, and I'm not so keen on equations. I prefer spreadsheets. So I put these into a spreadsheet, which is on the next slide. So next slide, please, Dennis. I feel like Chris Whitty. Those in the UK will know what I'm talking about there. That's it. Right, so I put those equations into a spreadsheet, which I call a course element spreadsheet. And the blue line is the calculated area. And the red line is the stress in the tether as calculated by my spreadsheet. So that confirms that the spreadsheet is working as it should because it shows a constant stress in the tether. So the blue line is the cross-sectional area, the red is the stress fixed to 88 gigapascal, which is the working stress, with a 20-ton climber at the earth port, with about 38-ton force at the earth port, which is enough to carry the climber, plus a bit of acceleration, plus a bit extra below the climber once it leaves. So that looks good, but it doesn't include the weight of the other climbers. If we're having a climber leaving every day, then and it takes a week to get to Geo, then there's going to be 6 or 7 climbers on the tether. This plot ends at Geo, by the way. It doesn't go all the way to the apex. So the next slide shows what happens when more climbers go on. The top line, the thick hashed line, shows the stress in the tether with the additional climbers in 24-hour intervals. And you can see the one that left 24 hours earlier is the one that does all the damage. That really pushes it up, and but the climbers a little higher have far less effect, but they still have a little effect. So the stress here is significantly higher. If we did nothing else and kept that base tension as it was, we'd need about 4,000-ton tether as opposed to about 2,700 tons tether. So I know Adrian would like to make more graphene for us, but even so, it will expensive to launch. So we need to try and work with the lower tether mass if we can. So one method would be to reduce the tension at the base, and that's the lower line. That's with the base tension reduced to, I can't read this, to 25 tons from 38, which is probably the bare minimum for a 20-ton climber. So that just about is acceptable, but it's still not quite there. You still need a little bit more mass in the tether. So we need a bit more stress reduction. So the next slide shows some other ways of doing it. We can get the stress down, but we would have to move to smaller climbers, to less massive climbers. And this is with 10 2-ton climbers leaving each day, as opposed to 1 20-ton. I know we want 20-ton climbers, but it's lifting the same payload, just in smaller batches. The green line shows the base tension down at, I'm trying to read this, it's so small on my screen, just above with a 10-ton base tension, and the lower one is with it reduced all the way down to just 3 tons, which is a very, very low value, but could perhaps be adequate for a 2-ton climber. But the question is, what is the minimum required force on the tether at the earth port? And that's where it comes into the atmosphere problem and the wind loading. So the next slide, please, Dennis, shows some of this graphics is from the 2013 book and also from John's paper presented in 2014, basically showing that if we had a 1 meter tether all the way to the ground, the force would be, we'd need 438 ton force at the base. even if we reduce the tether just to 4 centimeters, we still need 71-ton force, and that's double what we had before. So we'd need a tether twice the weight. Now, John and others propose the high stage 1, but that's new technology and technically ambitious. So I'm looking at perhaps another way of doing this. Now, I started looking at this as part of the interface study. It's fairly clear, though, that a 4 centimeter tether, which still needs double the tether size, it will be very difficult to get a climber to work with just a 4 centimeter tether. So it'd be very difficult to get a common design there. So we need to step back and think of another concept. And that's my next slide. So next slide, please. This is an alternative to the in-atmosphere ribbon tether. As we just said, the 4 centimeter tether would still generate wind loading, meaning a tether twice the weight, which we would have otherwise. And climbability is very difficult. So to minimize the wind load, it's better to go to a circular cross section, which is a cable. But how do you climb a cable? It's not easy, not with a powered climber. However, people have been using climbers for a long time to ascend many kilometers, and that is a cable car system. So my next slide shows how this might work. If you could switch the slide, please, Dennis.
Working on it. I seem to be frozen here.
Great. Oh, I thought I was for a minute then. So.
Don't know what's going on.
Maybe, Peter, you can just talk to what we would have seen.
Right. Well, the cable car system shows basically a pulley suspended on the main space tether at perhaps 60 kilometers altitude, with a 2 millimeter cable running over that pulley. The climber would be the climber or the climber components, because it probably wouldn't carry the full 20 tons in one go. We'd have to break it down into sections and assemble it above the pulley. Those sections would be assembled to the pulley node and then robotically assembled above the pulley to create a 20-ton climber, which would then depart each day at dawn to depart in the usual way from this new pulley node which I've created. And there is some graphics showing all that if Dennis can get that onto screen. I'm proposing using boron nitride, hexagonal boron nitride. I've got some numbers for that, supporting that. The only reason I chose that is that it's more chemically inert than graphene and is not electrically conducting. So that might be better, but it could be graphene just the same way. So is that the first one? Yes, that's it. So that's the preliminary concept: 2 millimeter cable, pulley node. There'd be a fixture on the cable of some kind to which cargo, which could be the climber or climber components or payload components. Those would be hoisted up to the pulley node. Target ascent, maybe 1 hour. It's 60 kilometers. That shouldn't be too difficult.
Are you seeing this now?
Yes, I can see it.
I'm just going to put it in this mode because I can move it.
Okay, that's fine. There's only a couple more slides now. So it would be easy to raise 10 2-ton sections and then assemble above the pulley node into the 20-ton climber. So I should have put numbers on these. I think that's the next slide. I think we can go on to the next slide now. So this is some numbers which I put together. 2 millimeter hexagonal boron nitride cable with a 6-ton force tension at the base, fairly modestly stressed at 18 gigapascal. It can take a lot more than that. The weight of the cable itself would increase that tension at the pulley up to 20 gigapascal. I've assumed a 50 kilogram mass for that pulley node, which includes an assist motor, which may be needed, and assembly transfer robotics. If you include a 20-ton climber just sitting above the pulley node, then the stress on the main space tether is just over 300 kilonewtons, which would yield with a 6.7 millimeter stress. I haven't got a graphic of the stress in the main space tether, unfortunately. And that would yield, using the normal taper ratio, we would then be within the 88 gigapascal at the GEO node as before. However, the mass of the space tether has gone up. It's now 4,300 tons. So we're back where we started, unfortunately. But we do have a way through the atmosphere, which is something. So I've just got one more slide that summarizes a couple of operational matters. If the winds are very light, we wouldn't need to use the cable car. We could just winch the pulley down to the ground or to the sea and launch the climber using the spring forward concept, which I won't go into here. But basically then the ascent in the atmosphere is powered by the stored energy in the main space tether. In medium wind conditions, yes, we'd operate it as a cable car. In high winds, in storm force winds, we probably wouldn't be trying to climb in any system. It may be necessary to replace these 2 mil cables with multiple wires of even smaller diameter to survive the very strong winds. But that's something that could be looked at in a bit more detail. And that's all I've got. That's my last slide. I don't know how long that's taken. So, thank you.
Great presentation, Peter. Thanks so much.